Okay, so let me kind of take you through what you're going to do on the slide. So what we're going to try and figure out is what's the different values of the coefficient of friction between different surfaces. So take a block of wood like A. So you're going to do wood on wood, aluminum, cotton, sandpaper. We're going to have two different values of the coefficient of friction, static and kinetic. So here's what you're going to do. The first thing you need to do is establish the weight of the block. How are you going to find the weight of the block? Hang it from boom, here, if you're like, it might be 3.76, whatever your block weighs. That column is not going to change. So once you get that done, boom, it's just going to be the same. To get the static friction, okay, this is the one that requires a bit of technique. So you're going to take the block, re-zero it, and then you're going to pull this thing until it just begins to slide. It's like in this case, that's 1.44 newtons, okay? So I would record here without however much force it took to pull it from rest. Then to get my coefficient of static friction, I'm going to take what it weighs, like in this case, I'd like take 3.76, whatever that number was, and then I divide it by how much force it took to pull it, and then that's going to be my coefficient of static friction. I don't need to see all of these calculations, but I at least want to see like the top row, okay? Then to get the kinetic, then you're going to take it, you're going to pull it along at a constant velocity, which is like 0.76 newtons. So here I'm going to record 0.76. That's how much force it took to pull it at a constant velocity. Then I'm going to calculate my coefficient of kinetic friction. Got that one. Next one is aluminum. So you take a piece of aluminum foil, lay that out, hold the aluminum foil, see how much force it takes to pull it from rest, then how much force it takes to pull it at a constant velocity. Same technique. Do the same thing then with cotton, which is a strip of this. Boom, boom, there you go. And then the last one you're going to use is sandpaper. All right? So which one, if you were to predict, which one do you think is going to have the highest coefficient of kinetic friction?
Sandpaper.
Sandpaper, that's the whole point. Okay? So that's going to be the first part of the lab. Then it's going to say draw a free body diagram of the block when it's being pulled on the wood surface at a constant speed. You're only going to do this out of all of this data for the block on wood and the constant velocity one. Okay? Not the kinetic, or excuse me, not the static one, just when it's being pulled. That's the only one you're going to draw. It's that one. But you're going to set up a scale. Hey, maybe 2 centimeters equal a newton. Do not draw these as tiny little vectors. It's annoying as all get out to grade. Okay? Now, then, and I tell you, this is going to be the first diagram. In big bold letters, I tell you, label every vector. You are conveying information about the lab. If you just draw an arrow, that means nothing. Okay? So your first diagram is going to look like a plus sign. Okay? You're going to have 4 vectors. Your force applied, your force friction, your force normal, your gravitational force. First one, going to be a plus sign. On the second one, I'm going to say draw the vectors using the tip to tail method. I always draw my gravitational force first. You're going to go down, there's my gravitational force. Boom. Force applied, force normal, force friction. That one should look like a rectangle. So the first one's going to look like a plus sign, the second one's going to look like a rectangle. Use the same scale. Okay? I don't care what you use, but use the same scale on both. Okay. That's the first part of the lab. Second part of the lab, we're going to add weight and mass to this block, and we're going to see what's going to happen. So what we're going to do here, this is going to be part 2. We're talking about kinetic friction, which means this thing is going to be moving. You're going to add the following mass to the block and determine the force normal and the force to pull it at a constant velocity. So here's the story. I'm going to take a 200-gram mass. Okay? I'm going to put it on the block. So you already know how much force it takes to pull this thing, just the block itself. You already have that number. So then I'm going to take 200 grams, I'm going to put that on there. So what does a 200 gram mass weigh?
Some newtons.
Some newtons. At least we're in newtons. That's a win. 200 grams is how many kilograms?
0.2.
0.2 times 9.8 gets you 1.96.
Yeah.
Okay. So I need the total weight that I'm going to pull. So I'm going to take on this line where it says your normal force, I'm going to take the block, which is like 3.76, let's just say. So I take 3.76 and then I'm going to add 1.96 to it. Put that on there, boom, I'm going to pull this thing at a constant velocity. So I'm going to pull this along, 1.42. So why do you think the force to pull it increased?
More mass.
Mass, okay? And we're like, it's like pushing your hands together like this versus pushing your hands together like this, right? So then you're going to add 500 grams. Take 500 grams, boom, put that on there. Now you're going to take 0.5 times 9.8, which is 4.9. 4.9 plus the block, boom, there you go. So you're just going to keep stacking more and more and more and more weight on top of it. This is not static. This is kinetic. Now, here's the story. You're measuring the applied force, but by default, when you measure the applied force, what else are you measuring? Force friction. So we don't directly measure force friction. So if I sit here and go, wow, that takes 1.71 newtons of force to pull it, that means my frictional force is negative 1.71, because that's how much I have to give to the gravity mafia. Okay? Got that. Okay, stop that camera. Let's go up.